So, hello everyone. Welcome to my talk. My name is Nicolas Schulz. I'm a senior rendering engineer at Crytek, and I'm going to talk about the rendering technology of Rise. But first, let me give a little bit of background on Rise. So Rise is one of the major launch titles for Xbox One. It is a close combat game which is taking place in ancient Rome. And it is a very story-driven adventure. We have approximately 2 hours of cinematics. The project has a pretty long development history. It started originally as a Kinect title in Budapest, but we did a full reboot when we moved it over to Next Gen in Frankfurt. With the development of Rise, Crytek was actually facing quite a few novelties. It is a very different type of game compared to the Crysis series, and it is actually our first console launch title, so we had to deal with a new evolving platform for the first time, really. And additionally, we were building up a completely new team for Rise, where just a few people had worked with CryEngine before. I should also mention that we just had a small group of rendering engineers fully dedicated to the project. So with Rise, we were facing quite a few rendering challenges from the beginning. With the upcoming Xbox One and PS4, it was the dawn of a new console generation. And Rise was early on meant to be one of the visual showcase titles for the Xbox One. Now, in this new generation, we had a problem we didn't have before so much, and that was that our hardware, our target hardware, was actually less powerful at launch already than some of the high-end PCs which were available. And so the major challenge with that is, how can you still get people excited for the new generation visuals? So if you're looking at Crysis 3, it is already a very rich game visually on high-end settings. And adding just more is not an option on weaker hardware. Also, we had the feeling that some things were already maxed out in the previous generation, like post-processing, where adding more effects just doesn't give you a visual benefit anymore. So what we did instead for Rise was focusing more on the consistency of the core components, and we worked on improving all the details. And this includes things like shading, the material definition, and the quality of our lighting and global illumination effects. In general, we were putting a strong focus on what you see all the time, as opposed to some specific features that you would just see every now and then. Specifically, what we wanted to achieve for Rise was trying to get away from a typical gamey look. The typical gamey look where you have no real material definition because you have a general lack of reflections, and where instead people are using overly high contrast to make the flat, diffuse materials look a bit more interesting. And we also wanted to get away from that over-the-top usage of post-processing, which was often used to cover other image deficiencies. And instead, we wanted to try to get a step closer to the aesthetics of CG films. And in CG films, you have very well recognizable materials and, in general, a very clean and soft image. And we thought that one key to achieving that is grounding the rendering more on physically based paradigms. And this is bringing us to the first topic of the talk, physically based shading. So physically based shading is a hot topic in this new console generation, and I assume a lot of you are at least to some degree familiar with it, so I just want to give a quick overview. The core idea of physically based shading is that the light-material interaction is based on real-world behavior. And it is quite understandable that this is giving more natural and more realistic results. And it also takes a lot of guesswork out of graphics programming. But one of the most important things is probably that it is enforcing some kind of consistency, because everything is obeying to one well-defined rule set. So when you start using PBS, you have considerable implications on several areas. The first one is the material model. We are now enforcing plausible material parameters, and we are discouraging unrealistic setups. We are having very clear rules now for assets, and ultimately this is leading to a lot more consistency on the content side, which is always a good thing for quality. The second area is the shading model. We are using more complex BODFs now. We are involving a Fresnel term pretty much everywhere. And we're, in general, thinking a lot more about energy conservation, like you have it, for example, with a normalization of specular highlights. The third area is the lighting model. And here, the most important thing is probably that you have to be careful that your lighting is actually not breaking your material integrity. If you're familiar with PBS, you certainly know that materials are set up using real-world reflection ratios. And now, if your lighting can randomly add some diffuse contribution without the corresponding amount of specular contribution, you're essentially changing that reflectance ratio and make it pretty much useless. So we found that physically based shading can only really work well if it gets respected in all of these areas. If you're lacking in one of the areas, you don't get the full benefit from it. So let's have a quick look at our material model. The most common attributes that we are using are pretty much what you would expect from a physically based renderer. We have the diffuse albedo. Ideally, diffuse maps should be calibrated. We didn't have time for that in RISE, so they were just eye-matched against the specular, which can work okay if you have an experienced art team. The next attribute is the specular reflectance. This is based on real-world index of refraction values. Of course, we also have surface roughness. And while this is actually a quite intuitive attribute, we found that when painting roughness maps, the inverse roughness is actually more intuitive because artists want to have bright colors where materials are more glossy. So we are actually having smoothness maps instead of roughness maps. And finally, we have a per pixel normal. We also have some special attributes, which are translucency and the subsurface scattering profile. And I will cover those a little bit more later. So this was a quick overview of a material model. Now let's take a look at the shading model we are using. We do have a unified shading model, which is expressive enough that the absolute majority of our objects can be rendered with it. For the specular BODF, we are using the quite popular Cook-Torrance microfacet model. And if you're familiar with PBS, you know that the Cook-Torrance model is comprised of a normal distribution function, which basically defines the shape of the highlights, a Fresnel term, which gives increased reflection at grazing angles, and a visibility term, which accounts for the self-occlusion of the microfacets. For the normal distribution function, we are using the GGX function. And the GGX NDF has become quite popular recently. And this is quite understandable because the function has a wider tail than other NDFs, like the Blin-Phong NDF, for example. And this leads to more natural and smoother and more natural looking highlights. And at the same time, it is still relatively efficient to evaluate. Now, for the GGX, we are remapping our roughness. And we are doing that to make the highlights more perceptually linear. On the one hand, this makes things a lot more intuitive for artists. But on the other hand, we are also filtering our roughness maps bilinearly and using MIP mapping. So we have to be careful that our input data is linear as well. You can see on the slide, down on the slide, the remapping function that we are using. And there's actually not a lot of science to it, but the reason we ended up using that function is that it has at least some similarity to a Blin-Phong exponent. And having a direct mapping can still sometimes be useful, for example, when you need to compute the Toksvig factor. Okay, for the Fresnel term, we are just using the Kamen-Schlick approximation, which is actually quite accurate for dielectrics. And for the visibility term, we evaluated many of the available options and ended up using the Schlick-Smith approximation because it takes into account the roughness and is relatively efficient to evaluate. However, we are also using a remapped roughness parameter here. The main reason is that we found that specular highlights are just getting too hot on glossy surfaces, but also at grazing angles, for our taste, the specular gain on rough materials was getting too strong. So we were reducing that. And this is mostly an artistic choice. Okay, this was the specular BODF. Now let's have a look at the diffuse BODF. The standard Lambertian BODF, which is used most of the time, is actually just a constant flat color. The MAF does involve the N.L term, but this is actually not part of a BRDF and is just accounting for the increased projected area at grazing angles. So for RISE, we wanted something which would take into account view dependency for diffuse as well, and so we were looking into an Oren-Nyer model. But Oren-Nyer model does take into account surface roughness, and it features retroreflection, which is light is getting reflected back in the direction from which it is coming. And this is probably not a massive quality improvement we are getting. It's subtle, but it's still a nice quality improvement for some rough materials like stone. It just helps a bit to break the standard look. Now, the original full Oren-Nyer model is actually pretty heavy to evaluate, but luckily there's some more efficient approximations available. Okay, this was an overview of our shading model. Now, one of the fundamental problems you have when designing a renderer is how you are applying your shading and how you are storing your shading attributes. And this goes down to deferred shading versus forward shading. Now, with RISE, we were starting from a Crysis 2 code base. And as some people might know, Crysis 2 was using deferred lighting or light pre-pass rendering. The idea here is that we are generating a minimal G-buffer with just normals and roughness. And then we are computing the irradiance and radiance in a deferred pass. And finally, we do another geometry pass, which is applying the material attributes. Now, with physically based shading, we do have a Fresnel term in our BRDF. And what the Fresnel term is doing is basically interpolating between the specular color and full reflectance at grazing angles. So this means the Fresnel needs access to a specular color, and the specular color is not stored in the minimal G-buffer. For that reason, deferred lighting just doesn't work well with physically based shading. And this was actually the main motivation why we were switching from deferred lighting to full deferred shading for RISE. As an added bonus, it also reduced the number of draw calls because we don't need the second geometry pass anymore. And that was actually also the reason why, in the end, full deferred shading made it into Crysis 3, but with some more aggressive G-buffer packing to better fit the previous generation consoles. So let's take a look at our G-buffer. We are using 3 32-bit render targets. In the first render target, we are storing the normals. And since our G-buffer format has just 8 bits per component, that's not enough for storing normals. You will see some noticeable bending. So we are encoding the normals using the best fit normal approach. The second render target contains the diffuse albedo, just stored as a flat color. Storing the specular color is a bit more involved. So the problem we are facing here is that we need to be able to blend to a G-buffer for decals or procedural wetness, for example. And if you have a multiple render target setup, you can't easily write to the alpha channel because in the shader, the alpha channel is containing your blend weight, at least not with traditional means, conventional means. For that reason, we want to be able to blend the roughness. This is very important, for example, for decals. Think of water puddles. So for that reason, we are storing the roughness in the first component of our second render target. And for the specular color, we are just splitting that up into a luminance and chrominance component. Now, the idea is that non-metal materials never have colored specula. So the luminance is enough, and we can handle blending properly for the non-metal case. We still can't blend the second chrominance component properly because it's stored in the alpha channel. So we are avoiding these cases on the art side, which is mostly related to metals. We are also storing some special attributes in the G-buffer. This is the subsurface scattering profile and the translucency. And we do have support for color translucency in the form of some transmittance filtering color. And for storing the translucency color, we are taking advantage of the fact that translucency is only really useful for non-metal materials. And those just have monochrome specula. So the chrominance components of a specula are free, and we can use those to store the chrominance of the transmittance color. We also do have support for some pre-baked AO, but we are not using that a lot in the end. Okay. At the beginning of RISE, we were also considering forward plus rendering. Now, forward plus rendering is pretty appealing because you can potentially save a lot of bandwidth since you don't have a G-buffer anymore. And this is especially interesting in combination with MSAA. However, in practice, there's still some open challenges. So one question is, for example, how do you handle surface modifiers like decals or procedural wetness efficiently if you can't blend them to a G-buffer anymore? The second thing is that forward plus requires a second geometry pass again. Otherwise, we can't cull the lights efficiently. And the next thing is that most research so far was just considering simple light models, mostly point lights. But in practice, we do have a lot more different light types. And this is leading to some quite complex shader code with a lot of branches. And if you have a lot of branches with dynamic branching, the number of general purpose registers is going up. And more GPRs means that your wave occupancy is going down, which can potentially hurt performance a lot. And we were afraid that this would happen a lot with forward plus. Another potential performance issue is that you're overshading and wasting performance with that, because due to how rasterization is working and the pixel shader is executed in 2x2 quads, tiny triangles can be rasterized more than you want them to be. I don't say that forward plus isn't a good option for the future, but for a launch title, we found it to be too risky. So what we ended up using is a hybrid approach. The majority of our objects is going through a full deferred shading path. And objects which have very specific shading requirements, in our case, mostly hair and eyes, those are rendered using forward plus. Okay, this was a part about our deferred shading and G-buffer considerations. The next thing I want to talk about is specular aliasing. And this is especially important in combination with physically based shading, because PBS is very prone to specular aliasing. The reason for that is that the BODF is producing some high luminance values. And that, in combination with high frequency normal information, can lead to some very ugly and annoying shimmering and flickering. Another issue is that when you are downsampling normal maps, you are actually discarding information. If you're averaging normals which show in different directions, you're losing the variance information. And the consequence is that, that a bumpy normal map is actually getting flat in smaller mid-maps. And to overcome these issues, we are strictly coupling normals and roughness in RISE. Now, this makes sense because conceptually, the two are related. Normals do represent the surface bumpiness on a macro scale, while the roughness attribute represents the surface roughness on a micro scale. To ensure that strict coupling, we are actually storing the roughness map in the alpha channel of a normal map in the source asset. In our texture baking or texture cooking pipeline, we are then extracting the variance from the normal maps and are baking that into the roughness map using the Toksvig factor. Now, this works pretty well. However, problems remain when we are updating the G-buffer on the fly, when we are changing the roughness in the G-buffer on the fly. And this happens, for example, when we are blending decals or when we are applying rain wetness. And in those cases, you get specular aliasing again, and we are addressing that by applying a normal variance filter in screen space. Now, this is a depth-aware filter to avoid issues at silhouette edges. And the nice thing is it does not only reduce the specular aliasing of normals, It also helps to reduce geometry aliasing on thin geometry. One issue with applying a Toksvig filter in screen space is that it can produce some noticeable outline artifacts, especially at grazing angles. I hope you can see them a little bit in the screenshot here. Now, we are mitigating that a bit by reducing the specular reflectance in those cases where you would have those outline artifacts, but you still can't fully solve that issue without more complex techniques. But anyway, we found the gain, the quality gain that you got in form of temporal stability to be a lot more important than those artifacts that you mostly just see on static images. So here in that screenshot, the G-buffer Toksvig filter is disabled, and you can hopefully see a little bit that there's a lot of little white dots, and in motion those are aliasing like crazy. They are flickering a lot. Now, if we enable the G-buffer filter, areas with high normal variance are getting a bit rougher. So the little dots are becoming less and they are more connected, and everything is more stable in motion. So it definitely does help for quality in motion mostly. Okay, the next thing I want to talk about is our light model. So for direct lighting, we are supporting the standard common types of light sources. But one thing I should mention is that we don't have an analytical area light model in RISE. Now, the main reason for that is that our scenario in ancient Rome doesn't require it so much because we have mostly natural light sources as opposed to artificial light sources. And natural light sources are not easily approximated by some simple geometric shapes like a sphere or a tube. Still, having some area for the light source is important with PBR because otherwise your specular highlights are getting very small. And to fix that, we are doing actually something very simple. We are just clamping the minimum highlight size in the BRDF. And this is of course not perfect, but it turned out to work good enough for us. Now let's have a look at the light attenuation. The traditional radius-based attenuation models that we were also using before are actually not looking very natural. The fall-off is too harsh, and you always have the feeling that you have a circle around the light source. So for that reason, we were switching to a more physically based attenuation model for RISE, which is computing the radiance emitted from a sphere. As you can see in the formula, the math does involve a bulk size parameter, and this is actually the real-world size of your light source, for example, a few centimeters. But we do also allow some unnaturally large values for the bulk size. And this can be useful for faking some effects like directional sunlight, where you actually don't have it really. Now, to make the attenuation model a bit more usable, we are normalizing the light intensity. And our definition is that the specified or desired intensity is reached 1 meter away from the light surface. So in the real world, light is actually traveling infinitely if it is not disturbed by something. It would be nice if we could do the same in engine, but unfortunately we can't for practical reasons, because we would run into performance issues since we can't color a lot of light sources anymore, and we would get light leaking because we can't afford having shadow maps everywhere. So we still need some cutoff radius. And since we don't want to compromise our physically based model too much, we are just fading out the light in the last 20% of a cutoff radius. So the remaining 80% still have the original physically based model. Okay, let's switch from direct lighting to indirect lighting. As I mentioned before, with a light model, it is really important to make sure that the lighting is not actually breaking the material integrity. And for that reason, we were dropping all of our constant and hemispherical ambient terms, because those just have diffuse contribution without any specular. And what happens if you use them is that your materials are just flattening out. You basically lose the specular. Now, most of our lighting is captured by localized environment probes. And where possible, the probes are augmented with screen space reflections to get more accurate localization. And we have another thing that we call ambient lights, which helps a bit to break uniformity, and I will cover that in a moment. So environment probes are making use of image-based lighting, and that is actually a feature that we have in CryEngine for a long time. We used it even in Crysis 2 already. But for RISE, we worked on improving the consistency with the analytical BRDF, and also we improved the usability of the probes. Our probes are placed manually at key locations in the level, and the attached cube maps are pre-convolved using a custom version of RTCubeMapGen. The probes are sorted by locality based on layers, so you can have more local probes which are overwriting more global probes, depending on where you want to add more detail to your lighting. We do have support for parallax correction using a geometry proxy, and this helps to get a better locality of reflections. Now, to make sure that the transition between two probes is not too harsh, we are computing a smooth blend weight. And our probes are not spherical anymore, but they are oriented boxes. And this helps to better fit them into indoor areas. Now, the question is, how do you compute a smooth fall-off for a box? And the way we do it is that we map the box up to a sphere first, and then we apply our attenuation function. Okay, now let's talk about the ambient lights. So one problem with environment probes is that they are actually just valid for one single point in space. But for practical reasons, they are being stretched over a larger area. But this means that you can miss some local light intensity changes. And this can result in some flat ambient. So the lighting artists need a way to more accurately set up bounce lighting. And what they first tried is using just regular light sources to add bounce lighting. But the problem is that then you get undesired specular highlights everywhere. The second thing they tried is just disabling the specular on those light sources. But then we run into the issue again that we are just adding diffuse contribution and we are flattening our materials. So we had to come up with something else, and actually our solution is super simple, and we call it ambient lights. Ambient lights are essentially just multiplicative light sources which are applied on top of probes. And the trick is that they affect both the diffuse and the specular by the same ratio, and so we keep the material integrity intact. Now, the intensity multiplier is pretty much working as you would expect it to work. If it's above 1, then you are brightening up the ambient, which can be useful for adding bounce lighting. And if it's below 1, then you are darkening the ambient, which can be used to emulate ambient occlusion. So here we have a screenshot where ambient lights are currently all disabled. And in the next shot, you can see that ambient lights are enabled. And the lighting artists are using the ambient lights here to emphasize certain parts of the image. For example, the statue in the front. And you can also see that they are using ambient lights to darken some of the back and just make the image more interesting. So this is a nice tool for the lighting team, and we don't have to be worried that they are breaking our materials. Okay, a similar problem with probes is that the locality is still very limited, even though we are using parallax correction. But a simple geometry proxy is still very limited in how it can improve the locality of reflections. For example, probes often can't capture small-scale reflections, and they also don't contain reflections from dynamic objects. So for that reason, we are exploiting image space information where available, which leads us to screen space reflections. Now, we first started experimenting with screen space reflections for the Crysis 2 DX11 patch. But for RISE, we worked a lot on improving the quality and especially making the screen space reflections work with rough materials. And this is leading us to glossy real-time local reflections. Now, if you want to generate glossy real-time local reflections, you have various options to do it. One possible solution is doing some kind of 2.5D cone tracing, which is conceptually similar to voxel cone tracing. For that, you are building a pre-convolved version of your scene buffer, and you're generating a min-max depth hierarchy, and use that while tracing along the reflection vector. Now, the cone width, which depends on the roughness and the ray distance, determines which MIP level you have to sample. However, for RISE, we opted for a simpler and also slightly cheaper solution. So what we are doing is we are just performing a simple ray tracing step, which gives us mirror reflections. And then we are building convolved versions of these mirror reflections by repeated downsampling and applying a Gaussian filter. Now, one trick is that the alpha is also convolved, and this makes unsharp reflections less visible. For applying the screen space reflections, the material roughness is determining which of our convolved version of the mirror reflections we are blending on top of the probes. And now this approach is clearly less correct than cone tracing. For example, it does not take into account the increased blurriness in the distance. But on the positive side, the reflections on rough materials are very stable because the convolution is done after the ray tracing step, and this is essentially like applying a low-pass filter. And for us, image stability was a big focus in RISE, so we opted for that solution. Okay, so this was the part about physically based shading. Now I'm going to move on to facial rendering. So RISE is a very story-driven game, and we have a huge amount of cinematics. So the quality of characters and facial animation and facial rendering in particular were a large focus from the beginning of the project. Now, on the technical side, we are mostly relying on our general shading and lighting improvements for characters and faces. But we also had to come up with some specific solutions. The first thing I want to talk about is skin rendering. Skin is mostly going through our unified shading model. And the reason this works is that the standard BRDF we are using in RISE, which is used on pretty much any material, is actually more advanced already than what was used for our NVIDIA Human Head demo back then. We also found, for example, that with a GGX and its fairly wide tail, highlights are looking pretty good on skin. And so we saw, for example, no urgent need to use multiple lobes to get smoother highlights, like it is done sometimes. So we didn't need a special solution here. One of the most important features of skin is certainly subsurface scattering. And for subsurface scattering, we are relying on a unified model. In RISE, basically any material can have subsurface scattering. And this is used a lot for marble. It helps to make the marble look a bit softer and a bit more interesting. But the subsurface scattering technique is optimized specifically for skin. And the reason for that is that we have a lot of close-up shots on faces. And also, you see errors in the skin scattering profile a lot more than on other materials. So let's have a look at the subsurface scattering technique. We are doing a screen space convolution, which is applied to a irradiance buffer after the lighting passes. And since this is happening in screen space, you have to be careful to take into account perspective distortion, field of view, and the aspect ratio to make sure that the world space scattering radius is actually constant. Now, our convolution is based on a separable cross-bilateral filter, as it was proposed by Morten Michelsen. And the idea here is that you have two Gaussian functions which are being combined. The first Gaussian basically takes care of blurring the image, and the weights are we use different weights for different channels to get the redshift of skin. The second Gaussian takes into account depth differences to make sure that we are not blurring across silhouettes. Now, the result of a convolution is one Gaussian again. And if you look at the skin scattering profile, it has a sharp spike and a broad base. And a single Gaussian lobe is not enough to approximate that. So your results will either look too blurry or too sharp. Now, you could do several Gaussian convolutions and blend those, but this is too expensive for us for real time. So what we do instead is we use the original irradiance to simulate the spike of our scattering profile, and we blend that with our Gaussian convolution, which takes basically care of the broad base part. And here we have a screenshot where subsurface scattering is disabled. And here we have our character with subsurface scattering enabled. So you can see the results are a lot smoother, of course, but still fine skin details like the pores are still relatively well maintained and not completely blurred away. Okay, another important feature of skin is translucency. And you have it mostly when light is bleeding through the ears or the nostrils. Now here again, we are mostly relying on a unified solution, which is shared with vegetation. The way we compute the translucency is quite simple. We are just using the inverted normal to estimate the amount of light that is entering from the backside. And then artists can specify some kind of thickness or density map with which they can block out certain parts where less light is passing through. As I mentioned before, we have support for transmittance filter color. And for vegetation, that can be an arbitrary color. And this helps to give a bit more saturation to a vegetation, which makes it look more natural and interesting. For skin, we are approximating the transmittance color using the specified thickness. And this helps to give us a more natural gradient. As you can see, the math is quite simple. It's just involving an exponential function and some hand-tweaked weights. And the results are visible on the screenshot, mostly on the ears. Okay, so this was skin rendering. The next thing I want to talk about is hair rendering. In general, hair shading is a quite well-researched topic. There's the standard model from Marshner, which is commonly used in high-quality offline rendering. And what Marshner found is that hair is actually exposing two highlights, which are shifted along the strands. The first highlight is coming from specular reflection, and hence it is monochrome. And the secondary highlight is due to light transmission. So it gets partly absorbed, the light gets partly absorbed, and hence the highlight is colored. Now, traditionally, in CryEngine, we are using a cheaper approximation, which is based on generating two highlights using the Kaya-Kai model. And we actually found that this worked pretty well, and continued using that solution because it gave good enough results. Now, what is important with both shading models is that you have a good direction map, which is specifying the tangent vector for your hair. so that you can shift the highlight in the right direction. The bigger challenge with hair rendering is actually how to make sure that the hair is looking smooth and how you avoid aliasing. And this is particularly true for thin individual facial hair, like you have it in sparse beards. For example, something like you can see in the screenshot here. Now, one option is using alpha testing, but the problem is that the hair will look too thick then, and it can look wiry, and you also run into an aliasing hell. The other option is using alpha blending. This does make the hair very smooth, and you get rid of all the aliasing issues, but you run into the well-known shortcomings of alpha blending. And those are that you get sorting issues if you don't have a solution for order-independent transparency. And also, since hair transparent geometry is usually not writing to the G buffer, you can't shade it in a deferred way, and you need to apply forward shading. The other issue is that some post-processing effects don't work with transparent geometry, because usually transparent geometry doesn't write depth, and then it's not available to the post-processing. So we were looking at, also looking at what other teams were doing, and one common solution for rendering beards or thin hair is using high MSAA sample counts. And while this can produce some very good results, it was not an option on the console for performance reasons, of course. So we did try out many variations of somehow blending opaque parts of hair with more transparent parts, for example, just making the tips of the hair transparent. But we never got the desired look for some types of hair. And for those types of hair, only full alpha blending really gave us the quality we wanted. So in the end, we had to bite the bullet and had to make alpha blending work with hair. And for that reason, we added a new feature, which we called thin hair. And this is specifically meant for hair which is not too dense, like you have it in sparse beards, for example, and where individual hair strands are visible. Now, the thin hair is fully alpha blended, so we don't have any issues with smoothness or with aliasing. Regarding the sorting, we don't have a technical solution here, so the sorting needs to be addressed on the art side. But in many cases, this is not a big problem. For example, if you have hair directly on skin, skin already acts as an occluder, so you don't get any sorting issues there. In other cases, we were mixing opaque hair, like hair caps or alpha-tested hair, with thin hair to reduce the sorting issues. Now, the shading is applied using forward rendering, actually forward plus rendering. And this was not a big problem for us because we are doing tiled deferred shading anyway, so outputting a light list just for the forward passes wasn't a big deal. Now, the last issue we had to solve was the post-processing. And we did that by adding something that we call depth fix-up. Now, the thin hair is not writing device depth, because otherwise we would get a lot of self-occlusion issues. However, when the hair is blended, the hair color is blended, we are writing an approximate depth value to the alpha channel of our main render target. And this approximate depth value is written using alpha test. Then, once all transparent geometry is rendered, we are doing a merge pass and are merging that approximate depth from the alpha channel with the original device depth. And the merged depth is then used for post-processing. And now the reason why this works relatively well is that all the alpha testing issues that you usually have, like aliasing or issues with the thickness, those are just less noticeable during post-processing passes, because post-processing passes are gather-based and are pretty much blurring away a lot of the issues. I should also mention that we are using the depth fix-up technique for some more opaque particles, like some smoke, for example, to make it work with depth of field. Now here's a screenshot which shows the depth fix-up disabled. And if you look at the top of the head of our character, you can see that the hair is very blurry. And this is because it is affected by the depth of field, which is blurring, which is out of focus in the background. And the problem is that the depth of field here doesn't have the depth information for the hair. So it assumes that the hair is in the background and puts it out of focus. Now with the depth fix-up enabled, you can see that the hair is properly working with depth of field now. And still, those hair strands at the top are very smooth. They don't have any aliasing, and they look very smooth and thin. Okay. So we're getting close to the final part of the talk, and the final part is some performance considerations. So probably the easiest way to reduce your GPU time is reducing the rendering resolution. For Rise, we were doing a lot of tests with different resolutions versus different quality settings. And for us, we found that 900p on the Xbox One is actually a sweet spot. It gives a good trade-off of quality per pixel versus the number of pixels on screen. So we are rendering our scene in 900p, but still our back buffer is 1080p. And the reason for that is that we want our text to be perfectly smooth and not have any upscaling artifacts, because we found it pretty important for a next-gen title. So our scene needs to be upscaled from 900p to 1080p, and we are doing that using a custom upscaling path. The simplest form of upscaling would just be doing a bilinear texture lookup, and we are basically doing that. But we are still applying a smooth step function to the texture coordinates before doing the texture lookup. And essentially what this is doing when you apply a smooth step function to a fractional part of a pixel coordinates is you get a mixture of nearest neighbor filtering and linear filtering. And since you have some nearest neighbor filtering now, you increase the sharpness of the image a bit. And we found the results to be pretty good. And the nice thing is it's also still very efficient. It's just a single bilinear texture lookup and a few allometric instructions for doing the math on the texture coordinates. We did not have time for Rise to evaluate the upscaler of the Xbox One, so I can't really comment on how it compares quality-wise. Another quite large optimization we were working on is tiled deferred lighting. Now, with conventional deferred shading, you have a problem that you use a lot of bandwidth because you have a lot of redundant reads and writes. You are reading always from a G buffer in your lighting passes, and you are writing the intermediate results to your light accumulation buffers. And this is wasting a lot of bandwidth. So one solution to overcome that is using tiled shading. And as you probably know, the idea of tiled shading is that the screen gets split into tiles. And we generate a list of lights affecting each tile and store that with each tile. And then to apply the shading, you just loop over the light list for each tile and do your shading math. Now this does help to save a lot of bandwidth because we're getting rid of all these redundant reads and writes. We are just reading the G buffer once at the beginning, and we are writing the results once at the end. And in Rise, we are using just a single compute shader, which is doing all the light culling and performs the lighting and shading. And this brings up some challenges. So the first thing is that when generating the light list, we are doing frustum culling against primitives. And frustum culling is not very accurate. It can create false positives. So in the end, we are often shading considerably more pixels than we would with a stencil volume-based approach. So we have to be careful that the benefit we still get from tiled shading would compensate that. Another challenge is handling the light resources. We need to make sure that all light resources are accessible from that one compute shader at a single point in time. And to ensure that, we are storing our shadow maps in a large atlas. Regarding the diffuse and specular cube maps, we are storing those in cube map arrays, which are then indexed from the compute shader. We have a similar problem with projector textures, and those are also stored in a texture array. One thing we found pretty tricky is keeping the general purpose registers under control. And I already mentioned it a little bit before. We do have a lot of different light types, and this leads to some quite heavy, branch-heavy shader code in the compute shader. Now, if you have deep branching, you need a lot of GPRs, and this lowers your occupancy. And we had quite a few problems staying within our GPR limit on the Xbox One. And in the end, we had to manually rearrange a lot of code to make sure we would really stay within the GPR limit and get the wave occupancy that we were looking for. But in the end, it was definitely worth implementing tiled deferred lighting. The average savings we are getting are between 2 and 5 milliseconds. And in some worst case scenarios, it can even be a lot more. So the last thing I want to talk about now is related to shadow maps and how we optimize shadow maps. We are generating something we call a static shadow map. And the idea here is that we generate one large shadow map which contains all the static objects. And this shadow map is generated at level load time. And when applying shadows, we are using that large shadow map as a replacement for the fourth and the fifth shadow cascade. And essentially what this does is it avoids that we have to re-render all the objects which are in the far away cascades. Now, we found that a resolution of 8K and 16-bit of precision is actually enough to cover a 1 kilometer area of our game world. And an 8K shadow map with 16-bit precision takes 128 megabytes. And this is something we couldn't have done in the previous generation, allocating such a big shadow map. So here we are really taking advantage of the increased memory on the new platform. And in the end, using the static shadow map helps us to save between 40 and 60% of our draw calls in the shadow map passes. So this is really a massive gain. So this concludes my talk. I want to thank you a lot for your attention. And I also have to thank a lot of people that made all this possible. And I think we're ready for questions now.
Hey, I have a question. I'm curious, how many lights were visible in the average case and the worst case in Rise?
Okay, in the average case, I would say it was something around 60 lights. In the worst case, we had up to 250 lights.
Quick question about the light attenuation model. So the bulb size, it's a separate parameter, so you still have the light radius, but you also have the bulb size, and they're not related in any way, right?
Yes. The bulb size is used for computing the fall-off, basically, of attenuation. The radius we have is really a cutoff radius, so that we artificially cut off the lighting in some distance just to make sure that we're not running into performance issues. So the cutoff radius is not taken into account when computing the attenuation.
Regarding the shadow map atlas, how big was the? I'm assuming you have like spotlights that cast shadows and whatnot.
Yes.
You had to pack all lights, all shadow casting lights of a frame in an atlas.
Yes, that's right.
How big was the atlas? And did you have any art restrictions on the number of shadow casting lights in a frame or something like this?
Yes, I think the size of the atlas was 8K. We definitely have some restrictions. We need to make sure that everything fits into that atlas. But then on the other hand, you can't enable too many shadow casting lights anyway for performance reasons. So that was not a big problem in the end.
Is the size of the shadow map per light something that's controlled by the artist or something that the engine automatically adjusts depending on the distance to the light?
Artists had control over how important a light is and how much resolution they want to have for the shadow map, how much space of the shadow atlas.
Thanks.
You're welcome.
I didn't hear you mention hardware tessellation at all. Is that something that you're doing anything with, like displacement mapping or anything with that?
We did not use any geometry tessellation RISE. We had some on the ocean, but not on meshes, on regular meshes.
Can you talk about any of the anti-aliasing solutions you used? Like, did you use any like FXAA or EQAA or anything like that?
For anti-aliasing, yes. We are using something we call SMAA1TX, which is a temporal solution. And if you want to have more details on that, Thiago Sousa was giving a great presentation at last SIGGRAPH where he showed some of the details.
Like the first is about the translucency on the skin, and in your talk you mentioned you use thickness map and use transcolor to glow it. I wonder how to avoid like glowing in the dark, some part like that, like because you character work around and some
Yes.
part is really dark.
Yes, that's a problem, and we pretty much ignored it. We tried to make sure that this is not happening on the art side. So the translucency solution we have is really simple.
And then the second question is how you guys dealing with the shadow for the hair? Because hair is an alpha blend shader, so they cannot use like a...
Yes, we are writing some alpha-tested shadow value for hair, and with the tiled shading we have access to the shadow maps of each light source, so we can apply some shadowing to it. To the hair.
So just disable the shadow on hair?
No, we do have shadows on some hair meshes.
Oh, cool. Thanks.
I have a question. You mentioned that you save 2 to 5 milliseconds on average on your deferred shading pass with tiled approach, and I was wondering out of how many milliseconds. So what was the cost of the compute shaders doing the deferred shading?
On average, it was like 5 milliseconds for the whole compute shader.
So it was 10 before and then it went down to 5?
In certain cases, yes.
Okay. Thanks.
Did you find, over here, did you find any advantages to the Xbox One hardware architecture?
We definitely made use of ESRAM.
Of the SRAM? And what about the unified memory and the GPU and CPU being on the same die?
We made some use of that for texture streaming.
Why don't you use tessellation on meshes? Is there any issues with it, or is it just artistic?
It was mostly an artistic decision. We could have used it, but in the end we didn't find a really big need for it. And also we were under heavy time constraints for RISE.
I have a request. Could you show a slide with rendered target setup again?
Sure.
So my question is, are you going to share the slides somewhere like you have done in the past?
Yes, definitely.
Can you give us the website? Or
yes, it will be on the Crytek website, Crytek/presentations or something like that.
Thank you very much.
A couple people asked about tests. Were there any other DX11 features that you guys particularly took advantage of? I know you mentioned Compute Shader. Was there anything that was above like feature level 9 that you particularly used?
The most prominent feature, DX11 feature, is probably the compute shader that we use. We're using UEVs here and there and some little DX11 features.
Graphics?
But sorry?
UEVs from graphics?
Yes.
Oh, okay, cool. All right, thank you.